In this video, we're going to go over section 3.2, talk about the slope and y-intercept of least squares regression line, and we're going to use the least squares regression line to predict y for a given x, and also talk about extrapolation. We're also going to define the difference between regression and correlation, and how the general equation in statistics looks different than maybe an algebra course. Let's start with regression versus correlation. Correlation has already been defined in 3.1. This is simply measuring, or it measures the strength and direction of a linear relationship. It knows nothing about variables or anything like that, context. It just knows numbers, how well, or what, as far as the strength and direction go of a linear relationship. Regression, though, is a little bit different, more specific. Regression summarizes the relationship between two variables but only when there's a specific explanatory and response variable. So this one's a little more specific. This one has some kind of relationship going on with regression in terms of what causes the other variable. Correlation is strictly just a bare bones, black and white measure of strength and direction of linear relationship. Sometimes students use them interchangeably, but they do have slightly different meanings. Regression lines. A regression line is a line that describes how a response variable y changes as the explanatory variable x changes. We often use these lines to make predictions. This is the big reason why lines are made. We can predict things into the future, given some certain set of data. Predictions are most accurate when correlation of these two variables is close to 1 or negative 1, and the value in the range is in the range of the explanatory variable. Predictions are less accurate with a correlation closer to 0. So be careful if you have a R value that's not that strong in either direction. Alright, so this table here is just going to show you the difference in how the equations look from algebra to statistics. In algebra, we did y equals mx plus b. M was the slope. B was the y-intercept. And those are the two variables of the equation, something you've seen quite a bit. In statistics, they like to do things the exact opposite direction. So they write their y-intercept first, A, and their slope with the x value second. There is no math change at all. It's simply cosmetic. So B is going to be your slope. A is going to be your y-intercept. Remember, your y-intercept occurs when x is 0. So we're going to be switching around the order here in statistics class compared to an algebra class, but the math itself does not change. Writing your equation, you might see the variables actually written out in words in the equation. That's no big deal. It's pretty standard. We're going to talk about some other notation within equations as well. You are feel free to use x and y, but make sure that you actually define x and y within the problem. So if you do use x and y, just don't lose track of what you're doing. If you forget what x or y is for the split second, you plug into the wrong variable, you're going to get some answer that doesn't make a whole lot of sense. Alright, this we're going to revisit in future videos. The least square regression lines makes the sum of the squares of the vertical distance as small as possible. Just a quick idea here. If I have some kind of scatter plot, anybody can walk up and draw a line, a regression line. And what the least squares regression line does is it finds all these vertical distances between the points and the line itself, and it squares those distances, adds them up, and it finds the line that creates the smallest sum. That's why it's the least squares regression line. So we're going to go into more detail about how that actually works, but that's essentially what a regression or a least squares regression line does. The computer does it for you. It finds the least or the smallest sum, but anybody can kind of estimate what the regression line will be. So using the equation to find missing variables is some not recommended, some recommended things you should do. If you're going to try to be accurate, don't read things off of a graph. If you're going to look at a scatter plot, it's good for estimating things, but do not use that necessarily to actually give a final answer. It can be dangerous if you do the graph by hand, especially. It's less accurate than an equation, and can still be used for estimation, but like I said, if you want to give a real accurate answer, you're not going to use it. What's recommended is you actually make a substitution into the equation. It's the whole reason why we make the equation is that we can plug something into it. It's way more accurate than reading the graph, but just remember that the accuracy also depends on the strength of the correlation. So your equation's only as good as your correlation. If your correlation is going to be 0.3, for example, just realize that when you plug in a number, it may not be as good as you think it is. All right, so on page 167, there is an example with a scatter plot for trucks and their price versus their mileage. And the equation is written like this. Price hat equal to 38,257 minus 0.1629 times miles driven. So unlike in algebra and statistics, we often write the variables right into the equation. It's no big deal. Some new notation. This symbol is pronounced hat. It's creative. It stands for predicted value. The actual value for your scatter plot will just be a plain old price or a plain old Y. If you put a hat on top of it, that's what we're talking about, is the prediction of what it should be if this line were accurate. So the accuracy of these predictions from a regression line depends on how much the data scatter about the line. In this case, prices for trucks with similar mileage show a spread of about $10,000. So keep that in mind. You have a range of possibilities. These scatter plots aren't going to be perfect. So we're going to try and make a prediction here. So let's find out the price of a truck with 300,000 miles on it. That's our prediction. 300,000 miles is what's going to go in for our x, or multiplying by our slope, then subtract it from our y-intercept here to find our y. So our predicted price for this will be 38,257 minus 0.1629 times 300,000. And this is a simple order of operations problem. 38,257 minus 0.1629 times 300,000. When you multiply that out, you get approximately a predicted price of negative 10,613. So when you make sense of this number, here's what it means. This means we need to pay someone $10,613 to take the truck. Think about that. I want to sell my truck. In order to get rid of it, I'm going to have someone, or I'm going to pay someone $10,000 approximately to take the truck from me. That doesn't make a whole lot of sense. And the reason it doesn't is because we extrapolated too far. We went too far outside the realm of the data, and therefore we have an answer that doesn't make any more sense than nonsensical stuff. So we have to be careful about what's called extrapolation. And extrapolate, think about the word extra, outside, prediction outside the data set. So you have to be careful with this. At a certain point, you can't go too far or it stops making sense. We actually have the graph in the book, and you notice the regression line looks like this. And in algebra, they go on forever. The lines do. They got arrows on the end of them. And that's not different in here either, but it's just, you have to keep in mind, you can only use it in a certain window. Once you get to this x-axis, that's your $0 mark here, $0. At that point, you'd be giving away the truck for free. that still would be something nobody would really do unless you're donating it for some other kind of reason. So there's really only a certain window you can use this from. So you've got to be careful with extrapolation. So let's write a bit about extrapolation. The definition is the use of a regression line for prediction outside the range of outside the range of values for the explanatory variable. We're going to put down here often not accurate. That's because we're using a model to predict something. Many people make predictions too far out where they should, so it ends up being not that accurate when it comes time to actually test it. But they can be a useful tool, so don't take the often not accurate statement as something you shouldn't be using it. It's just be cautious when making predictions. Taking all the facts. So besides the equation, you should be thinking about what's my R value? What's the correlation or coefficient? Should I really trust this prediction? If you do try to predict something or to extrapolate, try to only do it when there's data around the extrapolation point. So try to only extrapolate when you have data near the extrapolation point. So in the book, the data is something like this. Try to only do data around here. If you go too far out away from it, the prediction no longer makes sense. Okay. So you're going to be able to explain and interpret and calculate residuals, and then you're also going to be able to explain the concept of least squares. Explaining the concept of least squares is important to understanding where it comes from, because sometimes when you have to predict for a different variable, you'll understand the steps that we need to take in order to do so. So residuals in the least squares regression line. In an ideal scatter plot, the regression line will hit every single point. That's ideal. This does not happen in most cases. Nothing is perfect. There's all other factors that affect our data, so we're never going to get that perfect set of data where they line up exactly on the least squares regression line. So how is a line placed? How a line is placed, it depends on the residuals of the data set. And the residual is the observed y, so the actual data collected, subtract the predicted y. This comes from the regression line. So if you were to plug in your x value, what would the y value be? That's your predicted y. Or we can write it as y minus y hat, the difference. Okay? So this picture kind of illustrates it. Your measured value of the scatter plot, your predicted value would be the point right underneath it on the actual regression line, and the difference is the residual right there. So let's move on to another example from the book. This is not the graph of the example from the book. We're going to use the same exact truck problem before using the same equation. So we're going to use previous truck problem. You're going to find and interpret residual for a truck with 70,583 miles